Industrial manufacturing environments are defined by aggressive physical forces. Extreme heat, friction, and continuous vibration generate the raw inputs powering industrial analytics. But capturing telemetry in this environment creates deeply flawed data streams. Sensor outages, network drops, and gateway buffering create intermittent gaps, tearing holes in the data exactly when machines are under the most stress. Compounding these dropouts is heavy heteroscedastic noise, volatile, uneven static injected directly into the baseline signal by the physical environment itself. This vibration time series graph shows what happens when a standard machine learning model ingests this raw intermittent data directly. The model interprets the gaps in static as catastrophic mechanical faults, triggering an immediate false critical failure output. Naive data ingestion guarantees model failure. Before industrial IoT telemetry holds any predictive value, it must undergo rigorous, context-aware intervention. A common misconception in data science is that preprocessing happens in a centralized batch script, executed cleanly over a static, complete database. The reality of IIoT requires a spatially distributed preprocessing architecture, a physical pipeline stretching geographically from the factory floor all the way to the cloud. This architectural map displays three distinct tiers: the edge node at the machine, the local gateway, and the cloud data platform. This structure balances the need for low-latency operations near the physical machine against computationally heavy transformations in the cloud. Success in predictive maintenance relies on mapping the correct mathematical operation to the correct physical layer of this network. The first layer is the edge node. Embedded microcontrollers attached directly to the industrial casing operate under severe constraints, minimal compute power, and strict latency budgets that require responses in milliseconds. This chart displays a high-frequency vibration waveform captured at the edge, where jagged static obscures the mechanical signal. By applying a cheap digital filter, like a moving average, the local device strips away the static. This isolates the underlying trend without exhausting limited processing power. With the noise filtered, the edge device must address the second immediate problem: intermittent gaps caused by sudden sensor dropouts. Deleting rows with missing data is catastrophic for predictive maintenance. This practice destroys rare, brief indicators of early mechanical failure that are often the most valuable signals in the stream. This data stream plots sensor points over time, revealing a missing gap. To bridge these gaps on edge gateways without heavy compute, engineers rely on time series-aware imputations. A forward fill or spline interpolation calculates the missing values, maintaining a continuous data stream. The edge layer prioritizes speed and temporal continuity over deep statistical accuracy. It ensures that local, fixed latency inference models receive continuous data without overwhelming the physical device. Moving up the physical pipeline, data arrives at the local network gateway or 5G edge computing node. Here, multiple isolated data streams converge. At this ingestion point, unit unification and schema enforcement act as a gatekeeper. Converting Celsius to Fahrenheit or normalizing vibration scales prevents silent scale mismatches between different machine brands from corrupting downstream models. Here are two parallel timelines: continuous machine telemetry and discrete manufacturing logs. Misaligned timestamps obscure the relationship between temperature and operational state. Clock skew correction aligns these timelines perfectly, preserving the causal signals prediction models need to understand what caused the temperature spike. Standard statistical data cleaning can be counterproductive for predictive maintenance. By flattening outliers, these techniques inadvertently remove the very anomalies that signal impending machine failure. The pre-processing challenge here is differentiating between useless heteroscedastic sensor noise and transient, valid excursions that signify actual machine degradation. The solution relies on time series-specific anomaly detectors calibrated specifically for industrial drift. Exponentially weighted moving average control charts, or isolation forests, evaluate multivariate perspectives to accurately flag wear patterns. Firmly, outlier management in this context relies on provenance. Suspicious records are explicitly marked for review, ensuring they retain their entire lineage rather than being blindly deleted. Gateway preprocessing functions as a triage and alignment layer, ensuring that outliers are preserved as high-fidelity inputs for downstream analysis rather than being discarded as noise. Finally, the aggregated data arrives at the centralized cloud data platform. Here, strict constraints on local power are lifted in favor of massive compute scale. With abundant resources, the simple interpolations used at the edge are replaced with computationally heavy, model-based imputations used for batch retraining. This grid represents multiple parallel sensor streams. Multivariate imputation by chained equations, or MICE, analyzes cross-sensor relationships. It mathematically reconstructs missing pressure data based on correlated behaviors occurring simultaneously in the temperature and vibration streams. For mission-critical deployments, these imputations must be uncertainty-aware. Producing probabilistic confidence intervals allow human operators to override automated decisions when the model is mathematically uncertain. This standard 2D time series waveform is dynamically transforming into a 3D spectrogram. Heavy batch transformations, like fast Fourier transforms, extract deep vibrational signatures, isolating very specific frequency bands hidden entirely within the raw time series data. Ontology grounding then maps these deeply technical mathematical features to clear business language, ensuring that the enterprise analytics stack can reliably query and audit the data. The cloud layer sacrifices immediate inference speed for profound analytical depth. Its function is discovering long-term failure patterns to retrain and update the lightweight models governing the edge. This pipeline map connects the edge, gateway, and cloud tiers, showing the complete preprocessing architecture in real time. A raw, messy data pulse enters the edge, gets smoothed, aligns at the gateway, and exits as a structured, clean feature vector ready for MLOps. The success of this design lies in its spatial division of labor. Lightweight, streaming logic lives at the physical edge for immediate decision-making, while heavy multivariate modeling is reserved for the cloud to build deep intelligence. This multi-tiered approach balances strict engineering constraints. It respects local latency limits, conserves network bandwidth, and maintains high fault prediction recall. The overarching philosophy of predictive maintenance preprocessing is rigorous preservation, not just sanitization. Enforcing strict schema integrity and maintaining transparent feature lineage ensures that industrial models can be safely audited years after they are deployed. These rare, anomalous data points provide the high-variance signals required to predict catastrophic downtime. Erasing them as errors removes the model's ability to recognize failure precursors. Treating data preprocessing as a physical, distributed architecture rather than a single software script provides a robust framework for building predictive maintenance systems that can withstand the physical volatility of the industrial floor.